Welcome to the lecture series on CFD Part 1. This is Lecture 10 on Introduction to Solution Methods for Linear Algebraic Equation Systems. In this lecture, we shall first discuss the approach to solving the transport equations describing fluid flow and related phenomena. Although direct solution methods for linear algebraic equation systems are seldom used in CFD, I'll first describe two methods because one of them serves as the basis for some iterative solution methods. The next topic are iterative solution methods, which are almost exclusively used to solve algebraic equation systems in CFD. Because there are many of them, I'll first describe the principles of iterative solution approach and then present the simplest methods, Jacobi, Gauss-Seidel, and over-relaxation solvers. Line-by-line application of the direct solver for one-dimensional problems, the three-diagonal matrix algorithm or TDMA, will be described next. It is only applicable to structured grids. More complex are methods based on incomplete low-upper decomposition of the coefficient matrix. The basic algorithm is seldom used, but a version specially designed for the solution of partial differential equations, published by Stone in 1968, is efficient and widely used. It will be therefore described in detail. Finally, we shall briefly discuss iteration errors and their estimation. More details will come in Lecture 12, where the performance of different solvers will be compared and analyzed in detail. In Lectures 4 to 9, we have seen how transport equations can be discretized using finite difference and finite volume methods. The conservation equations describing fluid flow, heat, and mass transfer are in general nonlinear. The convection term involves a product of density, velocity, and the transported variable phi. Fluid properties like density, viscosity, heat conductivity, etc. are often dependent on temperature, pressure, or concentration. Source terms can also be nonlinear, especially in turbulence model equations. Nonlinear equation systems require an iterative solution approach. In the discretization process, equations are linearized so that in the end a linear algebraic equation system results in which only the transported variable phi is treated as unknown. The solution process involves then the following steps. We start with a guess for the solution, which is in most cases trivial, 0 or other constant value. We improve the solution by solving the linear algebraic equation system obtained through discretization and linearization step, that is, by freezing the coefficient matrix and the right-hand side. And then we update the coefficient matrix and the right-hand side for nonlinearity and coupling of equations for different variables and repeat until convergence. In this lecture, we are dealing with the second step, solving algebraic equation systems with a frozen coefficient matrix and right-hand side. Because this step is repeated many times until the outer iterations converge, the efficiency of the solver is important. Direct solution methods are often used to solve truly linear equation systems, for example, linear solid mechanics problems. No iterations are needed. The only remaining errors are those due to the arithmetic precision of computer, round-off errors. The computing effort is relatively high and increases over-proportionally when the grid is refined. Typically, it is proportional to the number of grid nodes cubed. Hence, direct solvers are seldom used for solving linear equation systems resulting from linearization of nonlinear equations. It is not necessary to solve linear equations so accurately in each outer iteration. One only needs to sufficiently improve the solution before updating the coefficient matrix and the right-hand side. Therefore, only a brief introduction to direct solution methods is given. The basic direct solver is the Gauss elimination. In it, equations are modified such that at the end an upper triangular matrix is obtained, which is easy to invert. The equation to be solved is square matrix A times vector matrix phi equal vector matrix Q. The coefficient matrices resulting from discretization of transport equations are always sparse, but Gauss elimination can also be applied when the matrix is full, as shown here. Inverting the matrix A for a large number of grid points n is difficult. Gauss realized that one can transform the matrix A to an upper triangular matrix, which is easy to invert. In this process, the matrix elements in all rows below the first are modified. This also applies to the elements of the vector Q on the right-hand side. To obtain an upper triangular matrix, one needs to eliminate all matrix elements below the main diagonal. This can be achieved row by row, starting with the second one and proceeding downward. We multiply the first equation, the first row of the matrix A, with A21 divided by A11, and subtract that equation from the second one. The first element of the new equation becomes the 0, while all other elements are modified, including Q2. We then proceed in the same way to the next equation, always multiplying the first equation with the ratio of the coefficient we want to eliminate and the diagonal element A11, subtract the two equations to obtain a new equation without the element below A11. This process is then repeated for the smaller set of equations starting with row 2, eliminating all elements below A22, and so on. At the end of the elimination process, we obtain an upper triangular matrix shown here. Elements in all rows below the first one are modified, but because the elements of the original matrix are not needed anymore, they are overwritten with the new coefficients. This part of the algorithm is called forward elimination. The last row contains only the coefficient a and n, so that equation is easily solved for phi n. Phi n is equal qn over a and n. With phi n computed, we can move one row up. That equation involves phi n and phi n minus 1, and because phi n is already computed, we can compute directly phi n minus 1. In the equation from row I, only phi I is unknown, because we have already computed phi for I plus 1, I plus 2 until n. Thus, phi I can be directly computed from this expression. This process is called back substitution. The number of operations required to solve a linear equation system of n equations by Gauss elimination is proportional to n cubed divided by 3. The costliest part is the forward elimination. The back substitution requires n squared half operations. For large matrices which are not sparse, Gauss elimination suffers from accumulation of round-off errors. The problem can be minimized by pivoting. Rows are interchanged to maximize the modified elements on the main diagonal. Fortunately, this problem does not show up for sparse matrices obtained in CFD. In principle, the matrix A can be factored into a product of one lower L and one upper U triangular matrix. To make the factorization unique, it is required that the diagonal elements of one of these triangular matrices all be unity. The elements of L and U can be determined by a modification of the Gauss elimination. We shall deal with that in the next few slides for a concrete case of relevance to CFD. Once the elements of L and U are determined, the solution process is very simple. We define the product of U and phi as a new vector y. This transforms the equation to be solved into Ly equal Q, which is easily solved for y by a forward substitution. Once y is computed, we can determine phi from the equation in the backward substitution step, the same as in the Gauss elimination method. When the matrix A is full, this method is as expensive as Gauss elimination. However, if A is sparse, the method can be very efficient and it serves as the basis for some good iterative solution methods. Let us see how LU factorization works for three diagonal matrices which result from discretization of one-dimensional problems involving only nearest neighbor nodes, for example, west and east. Such equations are obtained when using second-order discretization methods. High-order methods may result in a pentadiagonal matrix involving also WW and EE nodes. Their factorization into a product of L and U matrices can be easily performed following the approach described here for three diagonal problems. To make the factorization unique, we set the coefficients of the main diagonal of L matrix to unity as shown in this figure. We now need to determine the coefficients LW, UP, and UE such that the product of LU gives exactly A. How this can be achieved and the steps for solving the algebraic equation systems is shown in the next few slides. We now use the rules for matrix multiplication to determine the elements of the product matrix corresponding to the locations of coefficients AW, AP, and AE. The coefficient corresponding to AW is obtained by multiplying the coefficients from this row of L matrix with this column of U matrix. For the following coefficients in the row I, we move one column to the right and repeat the process. This leads to the following expressions. AW of row I is equal to the product of LW of row I and UP of row I minus 1. AP of row I is equal to the product of LW of row I and UE of row I minus 1 plus unity times UP of row I. Finally, AE of row I is equal to unity times UE of row I. From these expressions, we can determine the coefficients of L and U via coefficients of matrix A as shown here. The original equation to be solved, A times phi equal Q, can now be expressed as L times U times phi equal Q. We recognize that the product of the upper triangular matrix U and vector phi is another vector matrix which we denote as Y. By substituting Y for U times phi, the equation L times Y equal Q can easily be solved for Y during the forward substitution step. The rules for matrix multiplication with a vector lead to this expression for Y in row I. With Y computed, we can obtain the solution vector phi in the backward substitution step, starting with bottom of the upper triangular matrix and moving upward as described in slide 9. Because phi is already computed for rows below I, phi I can be computed directly from this expression. The solution method described in the preceding 3 slides is also called three-diagonal matrix algorithm, TDMA, or Thomas algorithm. The Fortran code for this solver contains only 7 executable lines. 4 are loop limits, and actually only 3 lines account for arithmetic operations. Because we only divide by UP, the reciprocal value 1 over UP is computed. LW is not explicitly defined because it is needed only at 2 locations, and I count on compiler recognizing that the same expression is used here and here, so that it is computed only once and reused. UE is also not explicitly defined because it is equal to AE. This is a direct solver for 3 diagonal matrix equations. No iterations are needed. The computing effort is proportional to n, the number of unknowns. A higher efficiency is only possible under special circumstances which are not of much relevance to CFD. For example, all elements on one diagonal of A being the same. There is no efficient direct solver for multidimensional problems. If we want an exact factorization so that L times U equal A, then L and U are not as sparse as A, and the computing effort increases drastically. On the other hand, there is no point in solving the linear algebraic equation systems in CFD very accurately, because we need the outer iteration loop to update the nonlinearities and coupling of equations for different variables, that is, to recompute the coefficients of the matrix A and vector Q. A good solver is the one which efficiently improves the solution sufficiently to keep the number of required outer iterations low, so that the overall computing effort is minimized. For the reasons just described, iterative solvers are almost exclusively used to solve the linear algebraic equation systems in CFD. Let us first see how iterative methods work in principle before presenting some particular solvers. Note that I call iterations used to improve the solution of linear equation systems with a frozen matrix A and vector Q inner iterations, to distinguish them from outer iterations where A and Q are updated. After n iterations, we have an approximate solution phi n, which doesn't satisfy the equation fully. There is a residual rho n. By subtracting the approximate solution phi n from the yet unknown exact solution, we obtain the definition of the iteration error epsilon n. If we subtract this equation from the exact one, we obtain the relation between iteration error and the residual, given by this equation. Solving this equation means driving residual to 0, and when this happens, iteration errors also become 0. An iterative solver is constructed using an iteration matrix M. It must be easy to invert, and it should be a good approximation of the matrix A. The original equation can be rewritten in this form. The contribution of matrix M cancels out when the exact solution for phi is inserted. However, during iteration process, phi on the left-hand side is the new estimate corresponding to iteration n plus 1, while phi on the right-hand side stems from the previous iteration n. Thus, the complete right-hand side is known, and the equation can be solved for phi n plus 1. If we subtract this equation from the exact one, we obtain the corresponding equation in terms of the iteration error at iterations n plus 1 and n. Sometimes preconditioning is applied. Matrix A and vector Q are multiplied by a non-singular preconditioning matrix P to improve the efficiency of the iterative solution method. The equation solved in the iteration process can also be rewritten in this form. Here, delta n is called the correction or update to the variable phi, and rho n is the residual vector computed with the solution from previous iteration. For an iterative solution method to be efficient, the following criteria should be met. The matrix M should be as good approximation of A as possible. That is, the product of M minus A times phi should be small, and the matrix M should be easy to invert. The following kinds of matrices are easy to invert: diagonal, tridiagonal, and triangular. The matrix M is not always explicitly defined. Here is a trivial example of an iterative solution approach. Imagine we want to solve the simple equation with a single unknown, A times x equal b, using iterations instead of a direct solution. We rewrite the equation by adding m times x on both sides of the equation and moving a times x to the right-hand side. After n iterations, the equation solved for x n plus 1 is given by this expression. When we subtract the above equation from the previous one, we obtain the following equation. By dividing both sides of this equation by m, we obtain a relation between iteration errors at two successive iterations. Rapid convergence is obtained if the iteration error at the step n plus 1 is much smaller than at the previous iteration level n. This is only the case if m minus a is close to 0, meaning that m must be a close approximation of a. Let us now have a look at some simple iterative solvers. The simplest of all is the Jacobi method. In it, the iteration matrix is a diagonal matrix whose elements are the elements from the main diagonal of the matrix A. The new value of the variable phi at grid point P is computed from this expression. The terms involving variable values at neighbor grid points are put to the right-hand side and evaluated using variable values from previous iteration, n. This solver is not efficient and is practically never used. The next simple solver is the Gauss-Seidel method. The expression for computing the new variable value looks the same as for the Jacobi method, but one uses on the right-hand side the latest available estimate for variable values at the neighbor points. If grid points are visited in lexicographic order, for example along grid lines from south to north boundary, starting at the west boundary and proceeding line by line toward east boundary, then at S and W neighbors the new values are already available. This corresponds to using the lower triangular portion of matrix A as the iteration matrix M. Obviously, M is not a good approximation of A because it is missing everything above the main diagonal of A. The convergence is better than the Jacobi solver, but still not good enough. An improvement is achieved by using an over-relaxation factor omega greater than 1, which gave the method the name successive over-relaxation. We effectively magnified the value that Gauss-Seidel method would produce by multiplying it with omega and subtract the value from the previous iteration multiplied by 1 minus omega. Values of omega between 1.6 and 1.9 usually work well. Omega equal 1 sets the method back to Gauss-Seidel. In multidimensional problems discretized by structured grids, one can use the direct TDMA solver along one grid line, considering the data from other grid lines as known. For example, like here. The left-hand side represents a three-diagonal system along a line from west to east boundary. Everything on the right-hand side is treated as known. We proceed line by line, starting with the grid line parallel to south boundary and moving towards north boundary. Variables at south neighbor have already been updated while solving for the preceding line, while variable values at the north neighbors are from the previous iteration. This approach is also called line Gauss-Seidel method. The marching direction is usually alternated from one iteration to another, first west-east lines, then south-north lines, then the same in planes from bottom to top in three-dimensional problems. Let us now see how one can create more efficient solvers for structured grids. The basic idea is called incomplete lower-upper factorization, or ILU. We choose as iteration matrix M a product of L and U matrices which have non-zero elements only on those diagonals where A also has non-zero elements. For one of these two triangular matrices, we set the elements on the main diagonal to unity, for example for the U matrix as shown in this figure. The problem is that the matrix M resulting from a product of L and U has two more diagonals than matrix A when two-dimensional problems are solved, as shown by dashed lines here. These two diagonals correspond to northwest and southeast neighbors of grid point P. In 1968, Stone proposed a special version of this approach which tries to compensate for the effects of extra diagonals. We shall see in the next few slides how this can be achieved. The rules of matrix multiplication give the elements of the matrix M equal LU in terms of elements of L and U listed here. Note that a single index is used instead of a pair ij indexes. The conversion is given by this expression. If nothing is done to compensate for the contribution of the two extra diagonals, that is, if we simply set the diagonals of M equal to the corresponding diagonals of A, the matrix M equal LU is not a good approximation of matrix A because it has two more diagonals with non-zero elements and convergence is not very good. This would be the original ILU solution method. Stone recognized that the method can be made much more efficient by allowing that the matrix M minus A has elements on all diagonals of N, such that the product of M minus A times phi gives minimized values in the resulting vector. The next slide shows how this can be achieved when solving partial differential equations with a smooth solution. The method is not applicable to arbitrary matrix equations. The extra diagonals in matrix M cannot be eliminated, but we can try to partially cancel out their contribution to the product of M and phi, such that the result is close to the product of A and phi. Stone realized that a partial cancellation can be achieved by defining approximations to phi NW and phi SE via values of phi at neighbor nodes, given by these expressions. The variable value at node NW is approximated as the sum of variable values at W and N minus variable value at P. The multiplier alpha is introduced to optimize the convergence. The value alpha equals 0.93 is often used. When these approximations are inserted into this expression, we obtain elements of M minus A as a linear combination of the coefficients M and W and MSE, such that the product of M minus A times phi is minimized. The elements of matrix M can now be set equal to the sum of elements of A and N equal M minus A, leading to these expressions for the elements of L and U. These elements can be computed directly when visiting grid points starting from the southwest corner of the solution domain, proceeding along each grid line towards north boundary line by line. Once we have the elements of L and U, we can solve the equation system using the procedure outlined in slide 12. As shown in slide 16, the iteration method can be expressed via variable update and residual, as shown here. Multiplying the above equation with the inverse of L, leads to the following expression for vector r, which in slides 9 and 12 was denoted by y. The elements of vector r can be easily computed in the forward step, because the elements at L-1, S neighbor, and L-nj, W neighbor, are already computed. In the backward substitution, we compute the update delta from this expression. Now the elements at L+1, N neighbor, and L+nj, east neighbor, are already computed. Here is the executable part of the Fortran code for Stone Solver. Note that the code shown here uses two index pointers, I and j, whereas in equations a single index is used. The conversion map is given by these expressions. In the first loop, the elements of L and U are computed according to these equations. Note that the reciprocal value of LP is computed because we only need to divide by LP. Here, the residual is computed as the difference between the right-hand side and left-hand side of the original equation, computed using variable values from the previous iteration. The absolute values of all residuals are summed up here to judge the convergence by the reduction of this residual norm with iterations. In this line, the elements of the vector r are computed. They overwrite the residual because residual values are not needed anymore. In this line, the elements of vector delta are computed. They now overwrite the elements of r. On the right-hand side, res is vector r. On the left-hand side, res is vector delta. Finally, the variable phi is updated by adding delta to it. The performance of this and other solvers will be examined in lecture 12. Iteration error is defined in slide 14 as the difference between the exact solution of the algebraic equation system and the iterative solution after n iterations. In section 5.7 in the book, an approach for estimating iteration errors is described. As shown in slide 14, iteration error is closely linked to the residual via this equation. This suggests that, except for the early stage of iterating, the error is reducing at the same rate as the residual. Residuals are usually computed anyway during the iteration process, so it is common to monitor their norm as a way of judging the convergence. The exact iteration errors can be determined by first solving the linear equation system until residual norm reaches round-off level. We then repeat the iteration process, and after each iteration subtract the intermediate solution from the exact one obtained in the previous step to obtain the exact value of the iteration error. Lecture 12 contains several examples of this procedure. Except for diagonal matrices resulting from 1D discretization, direct solution methods for linear equation systems require an excessive effort, increasing over-proportionally with grid refinement. Conservation equations are always nonlinear. The convection term contains a product of density, velocity, and the transported variable phi. If fluid properties are not constant, diffusion term is also nonlinear because of the product of diffusion coefficient and the variable gradient. The source term can also be nonlinear, especially when turbulence models are used. The linearized form of equations is not exact. Outer iterations are necessary to update the nonlinearity effects, that is, recompute the coefficient matrix and the source term. It is therefore not necessary to solve the linear equation systems to a high accuracy within each outer iterations. This increases the computing effort without reducing the number of outer iterations. The optimal solver is the one which improves the solution in each outer iteration just sufficiently. It may not be the best solver if a high accuracy was required. Examples will be presented in lecture 12.